All right, I want to look at section 6.9. It's very similar to 6.8 in that the book has a worked out example of a crank slider, and crank sliders are very useful as well. And so you can think of all these different labels on this graph as possible things that you can get rid of if you don't need them just by setting the numbers associated with them equal to 0. Okay? And so, for example, suppose I were interested in a compliant mechanism, and let's see here what we can come up with for this guy. I'm going to do a compliant link, something like this, and then I'll have a rigid link, and it'll have a short length flexural pivot. And so I'll have a crank slider mechanism. That's a compliant version of a crank slider that looks something like that. And so the pseudo-rigid body model for that guy is going to look like something like this. And I'll have a torsional spring here. And the value of that torsional spring, of course, is going to be determined by the information in Chapter 5, as will the one right here. I'll have a pin right there and a slider, something like that. And it'll also be a torsional spring there. And we call that one K3. And we'll just see what happens when we actuate that with a force X4, okay, on the slider. So if we have some sort of horizontal input on the slider. Okay, so that's the pseudo-rigid body model that we're going to look at. And so we've got a virtual work equation for this guy that we've got a virtual work equation that we can work with. There's a couple different versions of it here, but the one we can look at is equation 6.189 on page 250. Okay, and that'll just give us G21 A prime plus G31 B prime equals 0, and Q equals R1. That just means our input that we're thinking of is going to be R1. Okay. And so these G21 and G31 are kinematic coefficients. Those are up here on, so that's equations 6194 and 6195 on page 251. So those are just things we can look up because 4-bar is pretty standard. One thing to note on both this and the 4-bar, if we're going to use the kinematic coefficients, we have to define our vector loop in exactly the same way as Dr. Howe does in his book, okay? Because those kinematic coefficient definitions are based off the vector loop equations, and if we switch the directions of our vectors, it will change those equations, okay? So if you're going to do a 4-bar using these equations, you can't redefine the directions of your vector loops or the locations of your angles. You have to use the ones that Dr. Howe picked. All right, so these are just things that come out of, these are numbers that come out of the kinematics of the problem that we can figure out and just do the kinematics of a crank slider. So for this particular problem where we have a torsional spring, a source of potential energy, here K1 and K3, and then an input force that's doing work on this, X4, we can look at the definitions of this A prime and B prime. So A prime is defined, this is page 249, and it's equation 180. And so in our case, so A prime, first couple terms are x2 and y2. We don't have those. We do have in the next term an x4, so we'll just write down minus r2 x4 sine theta 2. We don't have an x2, y2, or y3, which is what shows up in the next term. We do have a t1 in this, so the next term we're going to get out of the A prime is just t1, and that's the torque associated with that slider, with this torsional spring. Okay, so this is just what A prime is equal to for us for this particular example. All the other terms go to 0 and are associated with potential energy inputs or force inputs, moments that we don't actually have in our particular problem, so they don't show up in our equation. And so A prime simplifies quite a bit for us, and that's pretty typical. For B prime, we don't have an x3, y3. We do have an x4, so we'll have minus r3 x4 sine theta 3. We don't have a x3 and y3, so the next term, next line, for this is equation 181 that I'm using to come up with the what the value of B prime is equal to. I don't have an M3 or a T2, but I do have a T3, so I'll have a plus T3, and I don't have an FS, so because there's no, I didn't put a spring on the slider. Okay, so so that's going to give us just that what our A prime and B prime are equal to, and then, so we can just substitute those into the equations. Okay, and so we're going to have G21. I can just leave it as G21 for now, times a minus R2 x4 sine theta 2 plus T1. And then I'm going to have plus G31 times minus R3. And this is just substituting in values of A prime and B prime into this equation that we have here. And so we have G2 minus R2 x4 sine theta 2 plus T1. And then we have plus G31 minus R3. And then we're just going to substitute that in, x4 sine theta 3 plus T3. And that's equal to 0. Okay, and so we can do a little bit more algebra with that. We really would want an expression for x4, and so we can think of just trying to isolate x4 as what we're going to do algebraically. And so it's convenient to leave all these terms just, I mean, they're these G21, T1, T3, G31, they can all be expanded, but there's no sense in doing that now because we still got to do some algebra to isolate x4. So let's go, because x4 shows up here and here. And so why don't we isolate x4 and then substitute in all those values. Okay, and so what we'll get is G21 x4 R2 sine theta 2 plus G31 x4 R3 sine theta 3 is going to be equal to G21 T1 plus G31 T3. And so I'll have x4 times G21 R2 sine theta 2 plus G31 x4, sorry, x4 should come out, R3 sine theta 3 is equal to G21 T1 plus G31 T3. And so we're going to get x4 is equal to GT1, G21 T1 plus G31 T3 over G21 R2 sine theta 2 plus G31 R3 sine theta 3. Okay.